morning. We are going to start on DC motor drives today. So this is lecture number 11. So first of all, we should remember that people have been predicting extinction of DC motor drives for the past several decades. In fact, from 1960s, people have been predicting that DC motor drives may not really be used too much, but still DC motor drives are being used in many applications because of one major reason. Speed control becomes really simple. So if you actually look at the AC motor drive, for AC motor drive, the only way to control speed is to vary the frequency. So voltage and frequency both have to be varied in an AC motor drive. And if you want to vary voltage as well as frequency, what you need is an inverter. Whereas in a DC motor drive, the power electronic controller or power converter, what we use could be a simple rectifier or it could be a chopper. So these two generally work or the design as well as implementation becomes much simpler. So that is one reason why DC motor drives are still ruling the roost as far as the variable speed drive market is concerned. So if we talk about adjustable speed drives, so in adjustable speed drives, generally DC was really ruling. But right now, after IGBTs especially have taken over the power electronic converter domain, now more and more inverters are being produced, because of which AC drives are also slowly coming into picture whenever we want a variable speed drive. If you really look at the cost of the overall DC drive, you have basically, there are two portions, as I mentioned. One is the motor itself plus the converter. These two are going to be very expensive, plus the accessories. So in the accessories, sensors, then control circuit, all those things. So this accessories will have sensors, then control circuits. These are going to be there. So all these things, if you look at for a DC motor drive, the motor is definitely more expensive than an induction motor. But if you look at the converter is generally less expensive. And also many of them may be made up of thyristors, and thyristors generally are not going to fail so easily. That's another major advantage that you might see when you use thyristor-based power electronic circuit. And if you look at the calculations involved, if DC motor drive, when you write the equation, you would write generally EB equal to K phi multiplied by I. K phi multiplied by omega. So when you write this, very clearly, flux is going to play a vital role in the back EMF. And if I'm looking at the torque is going to have K phi IA. So you can write basically that if I hold flux as a constant, if flux is a constant, speed is roughly proportional to the applied voltage. And similarly, torque is going to be proportional to the armature current. So in that sense, you would be able to decouple completely the flux and armature current control. Flux control, if you don't even implement, then only armature current control is good enough to control the electromagnetic torque. The same way, if I control the voltage, applied voltage, it is good enough to control the speed of the machine. So in that sense, decoupled control becomes possible. What we mean by decoupled control is armature and field. They can be controlled independently of each other. This is one of the major advantages we see in a DC motor drive. Whereas if you look at an AC motor drive, especially three-phase induction motor, you are going to have speed as 120 F by P. Synchronous speed is going to be 120 F by P. So where F is the frequency and P is the number of poles. So frequency necessarily needs to be varied if I want to vary the speed. The same way, if I look at the torque is going to be proportional to I square. And I is the current drawn from the stator side, which is also responsible for producing the flux in the air gap, and it is also responsible for the torque production, which is actually manifested as rotor current, and rotor current is actually producing the torque. So in that sense, it's not really decoupled. So decoupled control is not going to be very easy. So decoupled control is not easily implementable. So this is one of the problems we may face with AC motor drive. So that is one reason why when you look at the control algorithm for an AC motor drive, so the control circuit control algorithm for an AC motor drive is going to be definitely more complex. So on the whole, if I look at the cost of an AC motor, cost of an AC motor may be less expensive as compared to DC motor. But if I talk about the converter is again costly. So this will be costlier, definitely, as compared to the DC motor. And control methodology definitely is going to be more complex. So if I say control method, this is also going to be more complex. So these are the major problems that we are going to face with respect to the AC motor drive as compared to DC motor drive. And that is the reason why the DC motor drive had been always the first choice if we are talking about adjustable speed application. For adjustable speed application, always we are going to use DC motor drive. But now slowly with vector control and direct torque control, AC motors are also occupying that particular domain. So that is definitely slowly coming up. But nevertheless, like what it was predicted about 2-3 decades ago, DC motors are not going to be retired so easily, despite the fact that the commutator and brush assembly is one of the major issues for the DC motor, because that is going to require frequent maintenance. So this is going to require frequent maintenance. So this generally is one of the negatively impacting factors of DC motor. But however, for variable speed application, even now we are looking at a DC motor being used in many cases. Now let us try to look at the basic working of a DC motor drive. So DC motor drive also has two portions. Generally, the stator is going to accommodate the field or magnetic flux producing winding. So this is going to have the field system accommodated. So this is essentially going to work with V. If VF is the voltage applied to the field and RF is the resistance of the field, IF, which is the field current, this is going to be a constant. And as long as if we are not really looking at saturation creeping in, we are going to have IF is proportional to the flux. So if as long as IF is a constant, as long as IF is a constant, phi remains a constant. So we normally see that in most of the DC machines, the stator is going to have the field system accommodated inside that. And we are going to have the rotor, which is going to have the winding, armature winding. So this is going to carry a huge current. It is going to be applied with the voltage, and according to the kind of current that it is carrying, it is going to develop a certain amount of torque, because the torque is going to be proportional to some constant multiplied by flux multiplied by IA. So if we are keeping this as a constant, then torque is going to be proportional to armature current. Okay. Now, definitely we can have the structure reversed also. That is, the magnetic field can be in the rotor and the armature winding can be in the stator. It will still work. But generally, in most of the DC machines, we are going to see that the armature is generally going to sit in the rotor. So what we have is basically the armature winding will be connected to the external world with the help of commutator and brush assembly. So these are the two brushes that I have shown. So this is going to be the positive brush. Let us say this is the negative brush. So we are going to apply a voltage VA here, and the field could be a separate electrical circuit, which is going to I'm going to write this as F1 and F2. This is the field system. And I should be able to apply a separate voltage here, which is VF, and this is going to be IF. So how the field and armature are connected together, accordingly, we are going to have various types of DC motor. So if we look at the arrangement of field and armature put together, if the two are electrically not connected, then we call that as separately excited DC motor. So when the field and armature are independent of each other, they have separate power supplies. We call that as a separately excited DC motor. So if I am looking at IF, which is the field current is going to be equal to VF divided by RF, which is the resistance of the field winding. Now, the flux is going to be proportional to the field current if there is no saturation. So in a separately excited DC motor, in most of the cases, we might try to keep the flux as a constant, which means IF might remain as a constant, which means VF also we will keep it as a constant. Okay. Now, if VA is the voltage that is being applied here, and we are going to see that when the motor is carrying a current of IA, and because of the flux and IA, when the rotor starts rotating in a particular direction, then you are having a magnetic field within which these conductors are rotating. So the conductors are going to visualize a varying magnetic field, due to which you are going to have a d phi by dt being visualized by the armature conductors. So this is going to cause an induced EMF, which we call as the back EMF. And the back EMF is generally going to oppose. So the back EMF is going to oppose the applied voltage. So obviously that is going to have a plus here and it is going to have a minus here. So this is opposing the applied voltage. And definitely, although the winding is made up of copper, that there will be some amount of resistance manifested by the copper winding. So we are going to have whatever is the applied voltage for the armature, that is going to be compensated for by two components. One is the back EMF and the second one is IaRa drop. Okay. So this is going to be the fundamental electrical equation for the armature. So this is going to be the electrical equation for the armature. So once we write this KVL equation for Kirchhoff's voltage law equation for this DC motors armature, we already said that the back EMF is proportional to the torque is proportional to K phi Ia, and the back EMF we already said EB is going to be equal to K phi omega. So I should be able to write this as EB equal to K phi omega, where the K is actually a machine constant, which will depend upon whatever is the number of turns that we have in the machine, and then how many poles and what is the number of parallel paths we have for the armature winding and so on. So this is going to be K phi omega plus IaRa. But on the other hand, we said that the torque is going to be equal to K phi I. So I can write basically IA is equal to TE divided by K phi. So I should be able to write this equation, whatever I have got, this one as VA equal to K phi IA plus TE multiplied by RA divided by K phi. Okay. So in which case K phi omega. How did I write K phi IA? This is K phi omega. So I can write K phi omega equal to VA minus TE multiplied by RA divided by K phi. So I can write omega equal to VA divided by K phi minus TE by K phi whole square multiplied by R. So this is going to be the speed torque characteristics of a separately excited DC motor drive, as long as we are keeping flux as a constant. If flux is a constant, then this gives a straight line relationship. So speed, torque, relationship is represented by a straight line. So I should be able to draw this somewhat like this. If let us say this is the torque variation that I'm showing, and this is the speed variation that I'm showing. So I should be able to represent the nominal characteristics somewhat like this. So if I am talking about zero torque and a particular value of VA, the speed will be at this point, which is no load speed. So this will be omega no load. That will be equal to VA divided by K5. So as I increase the torque further and further, I'm going to have a steady drop in the speed. So this is the no load speed, and I'm going to have more and more drop in the speed as I increase the torque demand further and further. So if I am talking about a particular value of load torque. So let us say I am talking about the load torque somewhat like this. This is going to be the load torque. So the operating point is going to be somewhere here. This is going to be the operating point for this particular motor drive. When I'm talking about VA rated being applied, and I'm talking about rated armature being drawn and the load torque is being supplied, at that point, the speed must have come down slightly. So this will be the speed, which is omega rated or something like that. Now, if I talk about speed regulation for this machine, so the speed regulation is generally specified by how much is the drop in the speed from no load to full load. How much is going to be the drop in the speed? That's what we mean by regulation in the speed. The drop is going to be only about 5% of no load speed or even rated speed. So if I'm talking about 1500 RPM, right? So I will hardly have 15 multiplied by 5, 70, 75 RPM. If that falls, that is really, that is it. Nothing more than that. So you are not going to have much of speed variation in this particular motor. And one more thing, what influences the speed variation is RA. If the armature resistance is large, you are going to see that generally the speed is going to fall very rapidly. If the armature resistance is small, it is not going to fall rapidly. So if I am talking about large rated motor, that is maybe hundreds of kilowatt motor. In that case, if I'm applying only about 400 volts or 500 volts DC, then obviously I am going to require large IA. If VA is only 500 volts, then large IA. Because it is large IA, the conductors will be thick. The conductors will be really thick. So RA is going to be lower. So if RA is lower, then we are going to have the drop in speed. So in this particular case, drop in omega will be small. You will not see a large drop in omega at all. So you're going to see generally very, very low value of, regulation, speed regulation in this particular case, which is actually good for us, especially if we are looking at constant speed application. So the same characteristics can be drawn for what happens if I'm going to vary VA. So if I vary VA, this no load speed itself is going to vary subsequently. So the next characteristics may be somewhere here, another may be somewhere here, the next one may be somewhere here. So this will be for VA rated, this may be for VA dash, this may be for VA2 dash, and this may be for VA3 dash, where you're going to have VA rated is greater than VA dash, which is greater than VA2 dash, and so on. So when you are looking at armature voltage changing, the no load speed changes simultaneously at a particular load torque. You will be able to achieve different speeds depending upon what is the kind of voltage you are applying. So this is essentially taking us to armature voltage control for getting a control over the speed. So this particular equation, what we have written here, which is omega equal to VA divided by K phi minus TE divided by K phi square, the entire thing multiplied by RA. This equation tells us that one of the control variables could be VA. So armature voltage control is one of the methods which can actually achieve variable speed operation. So one is armature voltage control. The second type of control which you may incorporate to achieve variation in the speed is variation in RA. So you can increase the RA. You obviously cannot decrease RA further. So let us say this is the normal characteristics we are looking at. So this is TE and this is omega. And the normal characteristics I am showing like this. This is going to be the nominal characteristics. And let us say I am looking at a load torque value which is corresponding to this. This is TL. So this is going to be the operating point for my motor at nominal or inherent RA. Okay, and VA is at rated value. Now, if I don't change anything else, I'm only changing resistance. So let us say I'm having my armature here and field is on the other side. So if I am actually including a resistance, which is a variable resistance here, okay, so this is R external. So if I'm going to include something like this, then part of this voltage will be dropped in this particular external resistance and rest of it only will go towards applying across the armature or appearing across the armature. So in which case this drop, the entire reduction in the speed, that is going to increase quite a bit. The reduction in the speed is going to increase quite a bit. So the second characteristics which is corresponding to slightly higher resistance could be like this. So I can have multiple characteristics like this. So this is the operating point for the same load torque when I'm having RA plus R external 1. Whereas this may be RA plus R external 2. So I will essentially have this direction with R external increasing. So when my external resistance is increasing, I will have definitely a reduction in the speed. But please note that the external resistance is definitely going to have I square R losses. So in that sense, you are going to see that the efficiency of the complete drive decreases because of increase in resistance. So this is our armature resistance control. This is a very lossy method. So that is not really a good thing for us to use this method. So if we can somehow avoid using this and find some other means of controlling the speed of the DC motor drive, that would be much better. So let me talk about the third method, what we have, which we call as flux control or field flux control. So field flux control definitely is going to result in non-linear relationship between speed and torque because there is a K phi square here and the K phi is also coming in the denominator. So it's not going to be a linear relationship. So if I try to maintain RA as inherent value, and if I try to maintain VA at rated value, but flux is decreased from normal value. So if I try to reduce the flux, then what is going to happen is, let us again draw the characteristics. This is going to be TE and this is going to be omega. Okay. So I am going to have the characteristics somewhat like this. This is the nominal characteristics of the DC machine. And let us say this is going to be the load torque characteristics. So the operating point happens to be this. This is going to be the operating point. Now, when I am going to decrease the flux, the first thing that is going to happen is VA divided by K phi is the no load speed. This is going to be the no load speed. So this itself is going to increase if I try to decrease this one. So I'm going to have a characteristic somewhat like this. So if I try to decrease the flux further and further, I'm going to probably have the characteristics going. So they are not going to intersect at the same point. So the third characteristics, what I talk about, may have its value somewhat like this. So I can have multiple characteristics which are definitely not parallel to each other. They intersect with each other. And we are going to have different operating points for different flux values. So I may have one operating point here, one more operating point here, and one more operating point here. And if I'm talking about less torque, then probably my speed can really increase further and further as I decrease my flux further and further. So this direction is flux decreasing direction. When I have flux decreasing further and further, I will have speed increasing. So field flux control is one method which is very commonly used for increasing the speed beyond rated speed. If I want to go beyond rated speed, I should use generally field flux control. Whereas if I want to go for lower speed range, then generally we are going to use either armature voltage control or armature resistance control. So whenever I want to have speeds above rated speed, I may go in for field flux control. Whereas whenever I'm going to, make the motor run in lesser value of speed, in that case, I may use armature voltage control. Okay. So let us now look at another type of field connection. So we said separately excited. So field connections, what all we are going to look at. Field connections, whatever we are going to look at, or one is separately excited. The next one, which is very similar to separately excited, is shunt motor or shunt field connection. The third one which we will be looking at is series field. And when we combine series and shunt, we call that as compound motor. Okay. So in shunt field, as the name indicates, the field is going to come in parallel with the armature. So I'm going to have not a separate electrical connection, but these two are going to come in parallel with each other. So this is going to be the overall armature voltage or line voltage that I apply. So this is going to be the field current. And this is going to be the armature current. So what I see as the line current, that is going to be equal to IA plus IF. Normally, the field current will be about less than 10% of armature current. So we are going to say that IL is approximately equal to IA in the case of a shunt machine. IL and IA are roughly going to be equal to each other. And if I am not really going to change the current that is passing through the field, so if IF remains a constant, then flux is a constant. So I should be able to write the equation as again VA minus IA RA equal to EB, which is equal to K phi omega. So the equations become extremely similar to whatever we had for separately excited DC motor drive. So omega is going to be VA divided by K phi minus IA RA divided by K phi. And IA I can substitute for in terms of torque. So I should be able to write this as TE divided by K phi whole square multiplied by R. So this is going to be omega again. So shunt and separately excited DC motor both have similar torque speed characteristics. There will not be much difference between shunt and separately excited DC motor. As long as I'm not changing the field current value much, both of them are going to behave the same way. Whereas, let me try to give you a glimpse of series motor. So in a series motor, I am going to have, this is the armature. I'm going to have the field somewhat like this. So let me draw these two in series. So I'm going to just draw this, and this is connected here. And here is going to be VA. What I have got here is VA. So in this particular case, if I call this resistance as RF and this resistance as RA, I'm going to have VA minus RF plus RA multiplied by IA equal to EB, which is going to be equal to K phi omega. But in this particular case, you can clearly see that if I call this as IL, the line current, that is also the current which is flowing through the field, and that is the same current which is flowing through the armature. So I am going to have IA equal to IF equal to IL. All of them are going to be equal to each other. So I can say if IF is proportional to flux, I can say this is equal to some K dash multiplied by IF multiplied by omega. Okay. Now we wrote earlier that the torque is, electromagnetic torque is K phi Ia. So I have to write this as some K dash multiplied by IF multiplied by Ia. And if I'm going to say Ia equal to IF equal to IL, which is equal to some capital I have to write this as K dash multiplied by I square. So if I try to plot the variation of the torque, what is produced versus the current drawn by a series motor, I am going to have this to be parabolic variation. So the torque is going to be a parabolic function as compared to whatever is the current that is being drawn by the machine. Whereas if I try to look at the separately excited motor or shunt motor, we said that K phi IA is equal to TE, and flux is a separate entity. It is not going to have any dependence on IA. So if the flux is a constant, I'm going to have a linear relationship. So this is for series motor, whereas this is for separately excited or shunt motor. As long as flux is remaining as a constant, it is going to be a linear relationship between torque and the current. So now let me derive the relationship between what is the speed torque characteristics of the DC series motor. So I'm going to say K dash I omega is going to be equal to VA minus RF plus RA I'm writing as RSC together. Okay. Or let me just say that R, this as R. So minus R multiplied by IA. And IA is same as I because all of them are equal to each other. So I should be able to write I equal to TE divided by K dash square root of this. So I can write this as K dash I omega equal to VA minus R multiplied by I, right? Now, I should be able to write this as omega equal to VA divided by K dash I minus R divided by K dash. So this is one constant, let us say some C1, and this can be now replaced by VA divided by K dash, and I'm going to say this is root of TE, and on the top of this is root of K dash. So this I can together VA multiplied by VA divided by root of K dash I can call as another constant C2. So this is going to be C2 divided by root of TE minus C1. This is going to be the speed. So this is the torque speed characteristics of a series motor. So for a series motor, if I try to draw the torque speed characteristics, I'm going to have it somewhat like this. So let us say this is omega and this is torque. So when the torque is really, really low, the speed will be extremely high. And if the speed is really, really low, the torque could be extremely high. This is the way generally it is going to work. This is because if you look at the original equation, VA minus EB divided by R is equal to I in any of the DC motor. Now this EB depends upon omega. So if omega is low, EB is going to be really, really small. So if EB is small, I will be very high. And if I is high, the torque is going to be high because torque is proportional to I square. So that's why you are going to see that at lower speeds, you are going to have enormously large torque. And similarly, at higher torque value, if the torque value is very high, in that case, you are going to see that, you know, if the torque value is low, in that case, you are going to see that the current is small. Because the current is small, automatically you are going to have very, very low flux. If there is a low flux and you have applied a large voltage, you are going to ask for more and more back EMF. So in that case, the speed has to increase. EB is always proportional to omega and phi. And if the current is small, if torque is small, torque demand is small, demand is low, then I will be low. And if I is low, then I'm going to have flux will be low. So if flux is low, then to match EB value with applied voltage, a high speed will be needed. So whenever you are going to run the DC motor, series motor on a low torque demand, if you are going to run it on low torque demand, you will see that the machine really accelerates tremendously. So it is not advisable to run the series motor on light load. It's not advisable to run the series motor on very light load. So this is the crux of series motor operation. Now, if I am going to have, right, both series and shunt field windings, both series and shunt field winding. So let us say this is the motor armature, and let's say I have a series field winding, and I'm going to have a shunt across both the series field and the armature. So generally this connection is known as long shunt, because this is coming across both the field, series field, as well as armature. Whereas if I am looking at short shunt, so in short shunt connection, I'm going to have this as the armature. Now this is the field, and this field is coming only across the armature, and I'm going to have a series field beyond this. So this is short shunt connection. Okay. So this is the series field. So let me write that as R series. So here also it is R series, and this is going to be R shunt, and this is going to be R shunt. So what I'm applying here is VA. Let me call this also as VA. So when we are talking about the machine running very close to no load, you are not having any torque demand at all. So torque is proportional to IA. So under light load, IA is negligibly small. So if IA is negligibly small, we will have mainly only the field current flowing here. IA is almost going to be 0. So because of which the series field will also not have much of current flowing through that. So there will not be no series field influence in such a condition. So you would not see that series field is playing any role at all. It is primarily going to behave like a shunt machine. Here also you would see the same thing. If I say that this is IA, so IA is almost 0, and this is IF. And if I'm looking at what is the total current, that is going to be basically equal to IF itself. So I can say IF plus IA is going to be I line. So I line is going to be equal to IF itself under no load condition. So under no load condition, this particular or light load condition, that this particular machine will behave very similar to a shunt machine. Whereas once I start loading, as PE is increased or load demand increases, IA increases. Because IA increases, series field influence will take effect. And this series field can be wound in such a way that series field and shunt field together, both of them together, is going to be the total flux. So in such a situation, we call this as cumulative compounding. Whereas if I'm going to have shunt field minus series field is going to be equal to the total field flux, then in that case, we call this as differential compounding. So we can have either the two fluxes being additive or they are going to be difference of each other. So in that case, we can again look at the characteristics what we had. This was in characteristics, whereas this was the series machine characteristics. If I'm talking about, this is torque and this is omega. This is the characteristic for series, whereas this is going to be for shunt or separately excited. Now compound will be somewhere in the middle of the two. So whenever I'm talking about cumulative compounding, I'm going to see that the characteristics will be starting like this, but it will be somewhat like this. This is going to be the kind of characteristics I'm going to see. This can be nonlinear. So this is going to be cumulative compound motor. Because what happens in this particular case is we are going to have EB proportional to K phi omega. So omega is indirectly going to be equal to EB by K phi. And as the load torque demand increases, IA will increase, series field flux will increase. So phi total increases because this is equal to phi series plus phi shunt. That is going to be phi total. So phi total will increase. If phi total, flux total increases, that comes in the denominator. For a given voltage, speed is going to decrease. So for a given voltage, as phi increases, speed decreases. And that is what is seen here in cumulative compounding. Whereas in differential compounding, we are going to have phi total equal to phi shunt minus phi series. So we are going to have, when IA increases, phi total will start decreasing. How much it decreases depends upon the relative fractions of series field versus shunt field. So phi total will decrease. So if you may recall the original equation, we wrote omega equal to VA divided by K phi minus TE divided by K phi whole square multiplied by RA. This is what we wrote. So the torque, as torque increases, you are going to see a drop in the speed. But as torque increases, because IA increases, you are going to see the total fall in the flux, especially in differentially compounded motor. So you would see that there is a fall in the flux, because of which there could be an increase in speed. So on the one hand, the torque demand is going to reduce the speed, but on the other hand, the increase in the armature current is going to decrease the total flux, due to which the speed can increase. So you would see normally there will be an increase in the speed in the differentially compounded machine. But if I am designing the motor in such a way that the reduction in the speed due to the torque increase and the increase in the speed due to the reduction in the total flux, if both are cancelling each other, I would be able to get a speed which is fairly a constant value. So if I am talking about that as a constant value of speed, we call that as level compounded motor. Level compounded motor. So level compounded motor also should be differentially compounded machine, where the reduction in speed due to torque increase and increase in speed due to reduced flux, both of them cancel out each other. So this is a differentially compounded motor, which is a level compounded motor, is a type of differentially compounded motor. So this green graph also gives you differentially compounded DC. So differential compounding of DC motor can be used for obtaining almost zero speed regulation in the case of a DC motor, which will work as a compound motor, basically. So we had seen essentially four types of DC machine speed connection. One is separately excited, which is very similar to shunt machine. And the third one is series. And the fourth one is compound, in which both shunt and series will be present. So one of them could be differential, where the shunt and series fields oppose each other. The other one is cumulative, where we are going to have the shunt and series fields supporting each other. Instead of separately excited configuration, I can even install a permanent magnet, which is made up of ferrite or neodymium or samarium cobalt. Any one of the permanent magnet materials can be used as the source of field flux in a DC motor. So in that case, that will be called as a permanent magnet DC motor, where the excitation will be a constant. Flux will be a constant. Okay, so these are the different types of DC motor. We will also talk about different types of DC motor based on applications in the next class.